In section 2.3, we're going to start looking at some basic differentiation rules. So last section, we took a look at the definition of the derivative and how it applies. So earlier in this same chapter, we looked at the definition of the derivative. So we know that the derivative at a certain point is the limit as h goes to 0 of the difference quotient f of c plus h minus f of c, all divided by h. And if that limit exists, we say the function is differentiable at c. And we found that the derivative of this f of x was f prime of x. So the derivative of x squared plus 3x minus 2 is 2x plus 3. What we're going to do in this section is develop some basic rules and shortcuts so that we don't have to go all the way back and look at that derivative definition every time. So we don't want to have to recalculate this limit every single time. That can take a really long time, as we have seen. We're going to start developing some rules, and let's start with a linear function. Let's find the derivative of y equals 4x plus 9 using the definition. The derivative is the limit as h goes to 0 of f of x plus h minus f of x when my function is f prime, or excuse me, when my function is f. So the general rule, if I'm using y, just go y prime is equal to the limit of what happens when you plug in x plus h into this function. Well, when you plug in x plus h, you get 4 times x plus h plus 9. What happens when you plug in an x into that function? Well, you get 4x plus 9. All divided by h. We're going to utilize some algebra to simplify this limit. 4 times x plus h plus 9. I would distribute that 4 in. So 4x plus 4h plus 9. And then I'm going to distribute the negative sign in. That's negative 4x minus 9. Once we do that, we can combine like terms. And when you combine like terms, 4x cancels out with the minus 4x, plus 9 cancels out with the minus 9. On top, you're simply left with 4h. And on bottom, you have an h. So limit as h goes to 0. Obviously, we get a indeterminate form if we plug in h of 0. But I know that with limits, we can take and simplify 4h divided by h and go 4. And the limit of a constant number is just that constant number. So what we see there is we get y prime, the derivative, is equal to a constant of 4. Now that should make sense with our understanding of lines. This line had slope of 4. It was of the form y equals mx plus b. And that means the rate of change is always 4. Since the slope is always 4, the rate of change is always 4. So the derivative had to be a constant, had to be 4. If we think about how that's going to apply to other lines, well, we can simply use that same common sense we found, that if the slope of a line is 4, then the rate of change is 4, to figure out derivatives using common sense of these other lines. For instance, in example 2, we have two types of lines. We have g of x equals a constant, or y equals a constant. That's a horizontal line. And we have y equals mx plus b. That's a line with slope m. I'm going to start with g of x equals a constant. Think about that. That is a horizontal line, which means the slope is 0. And therefore, the derivative of g would be 0. So the derivative of any constant is 0 because this constant line, horizontal line, has slope 0. This line of slope m, it always has slope m. Slope is the rate of change, and it's a constant rate of change. So the derivative is always going to be m, just based on common sense. So derivative there is m. Now, this gives you an idea of how general rules are going to work. We're going to say, well, once we've figured this out, that if a function is equal to a constant number, the derivative is always 0, then I can just apply that over and over and over again every time I see a constant function. Or every time I see a line, I know now that the slope is the derivative of the line. So the derivative of the line is going to be a constant, and that constant is going to be the slope of the line. So I'm going to start giving you the general rules. Some of these I'll reference back to other things we've done. The general rules, there are a lot of general rules for taking derivatives of common functions. The rule that we just saw is often called the constant rule, that if k is a constant number, if you take the derivative of y equals k, the derivative is y prime equals 0. Again, horizontal line means slope of 0, so derivative of any constant number is 0. We saw that the derivative of a line was the slope. That's actually a couple rules together, one of which is called the power rule. The power rule is a rule which says if you have y equals x to a power, then y prime is equal to n times x to the n minus 1. Think about how that would work if the original exponent was 1. If the original exponent was 1, we would have y equals x to the first, or just y equals x. Now we know that that's a line with slope 1. Let's see if our rule fits that. Well, again, my exponent here is an implied 1. You can either write that as implied or specific. The 1 would come down in front. The x would get raised to the power, which is 1 less than 1. 1 less than 1, 1 minus 1 is 0. And if you think about that, x to the 0 is simply 1, as long as x is not 0. And so we see that the derivative of y equals 1. Now think about what that would mean if we had y equals x squared. The power rule would imply that y prime is equal to, we take this exponent of 2, we bring it out front, and then my new exponent is going to be 1 less than 2, or just, in this case, 1. And you can do this over and over and over again. Y equals x to the 14th. The y prime would be equal to 14x to the 13th power. So the 14 comes out front, and then x gets raised to a 1 less power. Now that's a really odd sort of rule of how that comes about, but we've actually seen this type of rule before. If you remember back to this function we found the derivative of, derivative was 2x plus 3. Notice that in part of the function there was an x squared, and that translated into a derivative which had a part which was 2x, and we had a part which was 3x. Notice that we translated that into a derivative which is a 3. That's like an x to the first. And then we had a constant part, and notice that that did not translate, that translated to a 0 in the derivative. And I'm alluding to another rule that we're going to look at in just a little bit that talks about how to add and subtract when computing derivatives. So the constant rule and the power rule are going to do a lot of work for us this semester. They're going to be very, very important, especially this power rule. We use that all of the time in moving forward. Other derivatives of common functions. Well, if you remember back, we took a derivative of sine and we got cosine through a big mess. But now we can just say, once I know y equals sine x, y prime is equal to cosine x. If y equals cosine x, it turns out through a big long process, you can find out that y prime is equal to negative sine x. These are ones that you will want to have memorized. The derivative of sine is cosine. The derivative of cosine is sine. The other ones that you'll probably want to have memorized is the exponential function. It turns out if we have an exponential function of base e, then the derivative of that function is also exponential function base e. So if y equals e to the x, then y prime is equal to e to the x. This is a really, really interesting one that it is its own derivative. We call this e sort of a natural growth. This is the reason why this e to the x is the natural base, if that makes sense. And we call this a natural log for the same reason. Log base e, when you take the derivative, you get 1 over x. So this number e is important. When we take a derivative of e to the x, you get e to the x. When you take a derivative of natural log of x, you get 1 divided by x. What I would like you to do is look at the functions on this page and utilize the rules of derivatives in order to find these derivatives. So don't use the definition, but rather use these shortcut rules that we've been developing.